Hey everyone, welcome back from spring break. I'm actually recording this before spring break, so hopefully the world hasn't gone too crazy over the past week. We're actually going to be on page 84 today, but I wanted to just review a quick couple of things that we talked about on page 83 because they're important on page 84, and I know it's been a long time, so you might have forgotten them. So remember, we talked about particles in solution. So we talked about when ionic compounds dissolve, and remember ionic compounds are a metal and a nonmetal. They break into smaller particles, and covalent compounds do not. And covalent compounds are made of two or more nonmetals. And then remember, we looked at a couple of examples here. So like NH3 is made all of nonmetals, so it's covalent, so it stays as one particle, it doesn't split up. But all of these ionic compounds, they split up into however many ions they're made of. So this one's made of 2, this one's made of 3, this one's made of 4. This one's covalent because it's all nonmetals. And then remember, this one had a polyatomic ion. So it only splits up into 2 particles because this polyatomic ion counts as one thing all by itself. Okay, so with that review out of the way, let's move on to page 84. And we're going to talk about something called colligative properties. So we're going to write down the definition of that first. Colligative properties. So colligative properties are properties that depend on the concentration of particles but not the type. Okay, so this will make more sense once we start talking about these different colligative properties, but just remember, it doesn't matter what the solute is, what you're dissolving, it just matters the concentration of particles. Okay, there's 2 colligative properties we're going to talk about. Number 1, and you should be taking notes along with me, everybody, on page 84. Number 1 is boiling point elevation. All right, so there's this thing that happens if you dissolve something in water, no matter what it is, it could be sugar, salt, anything that dissolves in water. If you do that, it is going to raise the boiling point of the water. So we're going to put adding a solute to water will raise the boiling point. All right, so people sometimes say that if you put salt in your water, it will make the pasta cook faster. And technically, yeah, it's going to raise the boiling point. So it might take you a little bit longer to get your water to boil. But once the water is boiling, it'll be boiling at a slightly higher temperature. So theoretically, maybe your pasta might cook faster. But it turns out the amount of salt that you have to dissolve in water to raise the boiling point by like 2 degrees Celsius is like a whole handful. It's like 250 grams or something like that. So if you throw that much salt in the water, then your water will boil at like 102 degrees Celsius instead of 100. So it's not really an effect that makes a big difference. Now, the more particles your solute splits into, the more the boiling point is going to go up. And we're going to see that in a second. But before we see that, let me tell you about one other colligative property called freezing point depression. So this is kind of the opposite of boiling point elevation. Elevation means to go up, so if you add something, the boiling point goes up. Freezing point depression means if you add a solute, the freezing point goes down. All right, and there's lots of applications of this. This is why we put salt on the roads, because it'll lower the freezing point of water, and so we won't have as much ice on the roads. In antifreeze, antifreeze is a mixture of water and another substance, and when you mix those together, it lowers the freezing point of your antifreeze so that it freezes at a lower temperature than it normally would, so you can use it in your car even when it's really cold outside. So, pretty important stuff. We're gonna write down something to help us remember that the more particles there are, the more the boiling point and freezing point are gonna change. So, we're gonna just write greater concentration of particles equals greater change in boiling or freezing point. All right, so on Canvas, you're going to have questions that are going to give you lists of different solutions, and you're going to have to say which one has the highest boiling point and which one has like the lowest freezing point. So let me just show you a couple of examples here. And we'll write one down in your notes, but not this one. So this says, which of the following solutions would have the highest boiling point? And I've got numbers, and then I've got a lowercase m, and then KCl. So you guys might remember that lowercase m stands for molality, which is a unit of concentration. That's moles over kilograms. So it's just a unit of concentration. You don't have to worry too much about it. Just know that that's molality. So we have 0.2, 0.1, and 0.3, and they're all the same solute. These are all an ionic compound. They're all going to break into two particles. So we're looking for the one with the highest concentration, because the highest concentration is going to give me the highest boiling point. So the answer to this one would be C. It's going to have the highest boiling point because it's got the highest concentration. Now, this one, we're actually going to write this one down. So, we'll do example 1. Which of the following would have the highest boiling point? And our options are 0.2 molality KCl. I'm going to move this a little bit here. Okay, so we've got 0.2 molality KCl, 0.2 molality NaCl, and 0.2 molality CaCl2. So you might at first look at these numbers and say, oh, these are all the same. They're going to have the same boiling points, but you have to look at how many particles these split into. So let's write down how many particles these split into. First of all, we need to check whether they're ionic or covalent. So KCl is made of a metal and a non-metal, so it's ionic, and since it's ionic, it'll split into two. NaCl is also made of a metal and a non-metal, so it's going to split into two particles. CaCl2 is also made of a metal and a non-metal, and it's going to split into three particles. So the way we can think about this, since this one splits into two particles, the concentration of particles is going to be double the original concentration. So you can just multiply this number by this number. So it's going to be actually 0.4. If we multiply these two numbers, this is going to be 0.4. And if we multiply these two numbers, this is going to be 0.6. Now technically, these concentrations are the concentration of particles. So the one that is going to have the highest boiling point is going to be this one, because it has the highest concentration. Okay, I'm going to give you just one more example, and and then we'll call it good and you can practice. So just so you know, if it's asking you for the highest boiling point, you look for the highest concentration. If it's asking you for the lowest freezing point, you also look for the highest concentration. All right, so we're going to do a freezing point one this time. So which of the following solutions would have the lowest freezing point? And we're going to have 4 options. That's aluminum right there. Okay, so this is going to take just a second, but then we're almost done. So the first thing we need to do is figure out whether these are ionic or covalent. So we already know NaC is ionic, NaCl is ionic from up here. CH3OH, that's all nonmetals. We've got H, which is a nonmetal, and CNO, which is a nonmetal. So that's covalent. Aluminum is right here, it's a metal. So this one is ionic. And we've already done CaCl2, so that one's ionic. Now we have to figure out how many particles they split into. So this one's going to split into 2. This one's covalent, so it doesn't split up, it just stays as 1 particle. This one's going to split into 4, because aluminum plus the 3 chlorines is 4. And this one will split into 3. And then what I should do is multiply my concentrations by the number of particles. So this one's 0.4, this one's 0.3, this one's 0.8, and this one's 0.3. So the lowest freezing point is whichever one is highest. So the higher the concentration, the lower the freezing point. So this one would be the lowest freezing point. Okay, so that's what you're going to be doing on the assignment. I know you guys can do this. If you have questions, submit a question on the Google spreadsheet or email me, or I can video conference with you over Zoom during my office hours. Lots of options for help if you need it. So, welcome back to school and good luck on your assignment.